Okay, this video is going to serve as an overview of hydrogen bonding, the third type of intermolecular force, and the implications that it has for water solubility. Okay, so if we look at this graph is going to look at different groups of compounds, specifically hydrides, which means the compounds of different elements with hydrogen. So it's going to look at those compounds moving down the periodic table. So we've got, this is period 3, period 4, period 5 elements on the periodic table, and we're looking at the trend in their boiling points. So, for example, if you were to look at group 14 of the periodic table, the element that's there is silicon in the third row, germanium below that, and tin below that. So all of these elements can form compounds with hydrogen, and they bond to the same number, 4 hydrogen atoms. So looking at these trends, it should be pretty clear that the boiling point is increasing as we move down the rows of the periodic table. And so if we had to try to explain that based on the IMFs we've talked about thus far, you should come to the conclusion that if the boiling point increases, that must mean an increase in IMF strength. That's just a general rule. More IMF strength means greater boiling point because the molecules are held together more strongly. So specifically for these, the main thing that's changing as we go down to further down rows in the periodic table is that with more principal energy levels with each row, we have greater atomic radii, so that the atoms are getting bigger. So the main thing that's happening, because the number of hydrogens is staying the same, is that as we go from silicon to germanium to tin, the central atom in this molecule is getting a lot bigger with each additional principal energy level. So we've got greater atomic radii. That means that the molecule has greater surface area. And we learned the other day that with greater surface area, we have greater amount of London forces. It's a type of IMF. So if we were going to attempt to explain this trend for really any of the groups, they all show increases as you go down the periodic table as the molecules get larger. So the boiling point increases, which implies IMF strength increases. That's because the atoms are getting bigger, so the molecular surface area is getting bigger, which increases the amount of London forces. So that would be bullet-pointed reasoning that you could give to try to explain those trends. Now, based on what you know about IMFs, if we had to predict where these 4 compounds would end up on the same graph, well, these are the compounds from group 2. So based on this trend alone, you should probably predict that for group 2, they would end up somewhere lower, like somewhere down here, somewhere down here, somewhere down here, somewhere down here. So just lower than the one to the right of them, because the general trend is that as we go this way, we've got increasing size of our molecules. Increasing size, increasing surface area, increasing London forces. So that's based on just London forces alone, that's what we would predict. However, go to the next page. When you actually look at those boiling points for those compounds, the methane one, the CH4 one, actually does sort of fit with the trend that we would expect. So it's the smallest of these 4, and so it ends up having the lowest boiling point. But these other 3 definitely do not fit with the trend that we would expect. We've got NH3, which is ammonia. We've got HF, which is hydrogen fluoride. And we've got H2O, which is obviously water. And they have much higher boiling points than we would have predicted based just on London forces alone. So the fact that they have much higher boiling points implies that they must have much stronger attractions between their particles. That's just a rule about boiling point. It also implies that the things we've learned about London forces or dipole-dipole forces alone can't explain why these are so high. So that is evidence that there's not just those 2 types of IMFs that we've talked about so far, London forces and dipole-dipole forces. There must be a third type of force, and it must be a lot stronger than the other forces, because these are tiny molecules, which means very limited London forces. So we would think they'd end up low, but whatever force they have is actually making them not only a little bit higher than we expect, but actually, in the case of water, right? Higher than any of these other molecules, even though they're way, way bigger. So it must be a pretty strong force. The name we give to that kind of force is hydrogen bonding. It is a misleading term, and I'm going to put it out there right now. When you talk about hydrogen bonding, you have to try your best to refer to it as an attraction or a force. It's just an IMF like London forces and dipole-dipole forces. It is not the same as an intramolecular bond. It's not a covalent bond. It's not an ionic bond. It's not a metallic bond. And if you refer to IMFs as bonds and you talk about bonds breaking and forming, the IB is going to ding you for that. So it's a really tricky vocab thing to watch out for because it's referred to as hydrogen bonding. Anyways, that's the point I wanted to get across there. So what is a hydrogen bond? When molecules contain really polar bonds, extremely polar bonds, and those bonds happen between hydrogen, which has an electronegativity of 2.2, and the really electronegative atoms of nitrogen, oxygen, and fluorine, which have values of 3 and 3.4 and 4 for electronegativity. They exhibit really strong forces of attraction between the molecules known as hydrogen bonds. Okay, so in order to hydrogen bond, you need to have this is doubly confusing because you need to have certain covalent bonds to allow you to form hydrogen bonds. The covalent bonds needed in order to be able to hydrogen bond is H to F, that covalent bond, or H to N. So like one of these, it's written in red here, N to H, right? That covalent bond, or O to H. Those are the covalent bonds that you need to have so that you can then form this other kind of attraction called an intermolecular force that is a hydrogen bond. Okay, so in all these drawings, I want to point out that the hydrogen bonds usually get represented as these dotted lines. And those dotted lines are always in between the molecules. So in the case of water, which is what's being shown here, this little atom here is a hydrogen. And this big red sphere here, that's an oxygen on the next molecule. So these are two different molecules. And the hydrogen bond is the thing that attracts those two things together. Same thing for H and F. So this is an HF molecule. These red balloon-looking things are orbitals holding electrons. And the dotted line here is the hydrogen bond, and it's attracting the H on one molecule to the F on the next molecule. Okay? Same thing for the ammonia. The covalent bond is between the N and the H. That's inside of a molecule. The hydrogen bond is this dotted line that goes from the H on one molecule to the N, the lone pair on the N on the next molecule. So occasionally you get asked to draw an illustration of a hydrogen bond, and what they're looking for is that it's between the correct atoms, so NH, OH, or FH, but also that you're not pointing to the bond inside of a molecule. It's the dotted line that goes from one molecule to the next molecule. And so it always goes from a hydrogen on one of the molecules, and then you draw, like I usually draw little dashes, and it goes to the lone pair on N, or on, it could have been O, or it could have been F on the next molecule. But this thing here, these dotted lines I just drew, that represents the hydrogen bond. So it's very, very, very important with the hydrogen bond that you understand it's not a covalent bond. Okay, there can be more than one hydrogen bond per molecule, which is why I included this to show water. Water, because every water actually has two lone pairs on the oxygen and two hydrogen atoms off of the oxygen. Each water can form a maximum of 4 hydrogen bonds. And so that's actually what you have in solid ice. Water takes a very regular arrangement, and every single water molecule is forming 4 hydrogen bonds with its neighbors in a nice tetrahedral arrangement. It's actually the reason why ice is less dense than water, because in ice, every single water molecule is spread out from its neighbors with this distance of a full hydrogen bond. Whereas in liquid, when the water molecules are moving around, they form some hydrogen bonds with their neighbors, but they don't form hydrogen bonds they don't all form 4 hydrogen bonds. So they kind of clump together, and those little clumps can actually get closer together than when they're all forming hydrogen bonds in all directions. So this is like this very fragile ice structure with 4 hydrogen bonds in every direction. And then as you heat it up, some of those hydrogen bonds break, and you start to get these clumps of water molecules that can move closer together. So it's actually why ice floats on liquid water, which is very unusual for a solid and a liquid. When water is in the gas phase, it doesn't really have any IMFs happening between its molecules because they're all moving too fast and they're too far apart. One other consideration for hydrogen bonding. While H to N, H to O, and H to F bonds, so I usually say instead of you have to have enough, the word enough to hydrogen bond, I say you have to have H enough to hydrogen bond. So you have to have H to N, H to O, or H to F somewhere. Those covalent bonds need to occur for then the hydrogen bonding to occur. But you actually can have hydrogen bonds happen with molecules that don't have those bonds. And so if you have 2 different molecules, this is possible. So to illustrate what I mean, so over here on the right, this is one of the examples of an H-nuff bond, an N to H covalent bond. Okay? Now, over on the left, this bond is not an H-nuff bond. It's just a C to O bond. It's a polar bond, but it's not actually a hydrogen bond, or it's not actually a covalent bond that could lead to hydrogen bonding. However, because I have an H-nuff bond over here, you can actually form a hydrogen bond with this oxygen on the next molecule. So hydrogen bonding is possible so long as one of the molecules involved has an H to N, an H to O, or an H to F covalent bond. So this bond over here is what allows a hydrogen bond to form between this H and that oxygen. Okay, same thing can happen here. Once again, this bond is providing the H-nuff bond, and this one is not, but a hydrogen bond can still take place between them because of that first H-nuff bond. And one more time, only this one is providing the H-nuff, but this N on the neighboring molecule could form a hydrogen bond with that H. Okay? So there are going to be some implications of that. One implication is that if you have molecules like acetic acid, or ethanoic acid as we're going to call it, ethanoic acid has a carbon, it has an OH group, but it also has just an O. Okay? But as a result of having both an O and an OH group, it actually has 2 locations for hydrogen bonding as opposed to just one. So it can form hydrogen bonds between the OH on one molecule and the lone O on the next molecule. And then it can also form from the H on this molecule to the O on the other molecule. So each molecule can actually now form up to 2 hydrogen bonds with each other, as opposed to this molecule on the right, which is ethanol. And ethanol just has one OH group. So ethanol can really only form 1 hydrogen bond per molecule normally between the 2 OH groups. So by having that extra oxygen atom, even though it's not bonded to an H, because of the OH group has H-nuff, you can form these additional hydrogen bonds in the ethanoic acid. So the more sites, the more places there that can form hydrogen bonds, the stronger the overall hydrogen bonding in the molecule, and therefore the higher boiling point. So even though these are pretty similar in size molecules, the one that has this additional space for hydrogen bonding, we would say, should have a higher boiling point because it has a greater ability to hydrogen bond. It's also going to have implications for water solubility. Water can form a lot of hydrogen bonds, so it tends to attract other things that can form hydrogen bonds like this ethanol molecule. But water can also now form hydrogen bonds with things that don't have O to H bonds or N to H bonds, something like this dimethyl ether. It has an oxygen in it, and therefore a hydrogen bond can form between water and this molecule, even though this molecule on its own cannot form hydrogen bonds. So DNA is a super important implication for hydrogen bonding. Hydrogen bonding is how the bases, the letter code of your DNA holds itself together. It's how it replicates, and it's because certain bases actually fit together with other bases based on hydrogen bonding, whether or not they can form 2 or 3 with one another. So it's pretty cool how they end up fitting like a little lock and key with one another, and that's what holds giant chains of DNA together. So not really on the syllabus, but just kind of a nice implication. A really important new physical property to think about when you talk about hydrogen bonding is water solubility. So water is a really good solvent. It's not a universal solvent. An important rule to remember with solubility is that like dissolves like. And so polar things tend to mix well and dissolve well with things that are polar, and nonpolar things mix well with nonpolar things, and they don't mix well with each other. But the new rule is that hydrogen bonding mixes really well with other things that can do hydrogen bonding. So as I showed this picture before, water can form a lot of hydrogen bonds with itself. And that means that water attracts itself really strongly. So substances are only going to be able to mix with or dissolve in water if they can attract water as strongly as it attracts itself. So the types of compounds that are going to actually end up being water soluble are those that are ionic, compounds that have full ion charges, or molecules that can form hydrogen bonds with water. So when you have ionic compounds, the water molecules will, the polar water molecules will attract the ions and pull them out of their lattice in what's known as an ion-dipole interaction, the ion charge and the dipole charge of the water. So most ionic compounds end up being soluble in water. For molecules, though, the ones that are going to be water soluble are ones that are relatively small and have H-nuff bonds in them. So things like ethanol. Alcohol is very soluble in water, 100% soluble in water, because it has its own H-nuff bonds, and water obviously has the H-nuff bond, and so then between them, you can have hydrogen bonding. But as I explained before, there are also going to be molecules that can dissolve in water if they are relatively small and they contain NO or F atoms. So they're polar molecules on their own. If you ignored the water and you just looked at the dimethyl ether molecule here, you should identify that it's polar from this bond, and so it would have dipole-dipole forces. But with water, because water provides this O to H requirement, this really superpolar bond, you can now have hydrogen bonding happening between water and this other molecule. So the types of molecules that are soluble in water are small molecules that have H-nuff bonds or that at least have NO or F atoms, because they can both form hydrogen bonds with water molecules. So in an answer, you would want to point out, why are these things soluble? Because they can form hydrogen bonds, and you have to specify with water molecules, always on the mark scheme. Factors that affect water solubility, the main one, especially for organic compounds, is that being able to hydrogen bond is important, and the more places you can hydrogen bond, the better. But also the length of the carbon chain matters. So this is a data table on solubility in water for alcohols. And as you can see, we start with these really small alcohols, 1 carbon, 2 carbons, 3 carbons. So they're getting longer each time. And as the carbon chain increases, you notice that at first they are infinitely soluble in water. You can add as much of these things to water as you want, and they'll keep mixing. But then actually very, very rapidly, tiny, tiny amounts of them will dissolve. So solubility is dropping. And so the reason why that is if you think about it, the water is really only attracted to the OH group. That's the only part of it that it can form hydrogen bonds with. So the smaller the molecule, the better water can surround this molecule and dissolve it. As the chain, the hydrocarbon chain, or the non-polar part of the molecule, which is what the C and H part is, it's completely non-polar. Water doesn't attract that part. It doesn't mix with that part. So as that part of the molecule gets larger, the molecule will get less and less soluble because water can't dissolve it as well. So the main implication for water solubility is that as the non-polar part of the molecule increases, usually as molecules get larger, they get less water soluble. Just some final IMF considerations. This is a bit off topic from hydrogen bonding. So far, we've talked about hydrogen bonds, we talked about dipole-dipole forces, and London dispersion forces. Those are the 3 main IMFs that you have to discuss. There are other types of interactions technically. So we just mentioned ion-dipole interactions is what happens when a polar molecule and an ion attract each other, like when water dissolves an ionic compound. Ions can technically come near nonpolar molecules and induce a little bit of a dipole in them. That's called an ion-induced dipole force. And polar molecules can induce small dipoles in nonpolar molecules, and that's called a dipole-induced dipole. I only point this out because on the old syllabus, there was a term van der Waals forces that got used in place of London forces. That's no longer accepted. And technically, dipole-dipole forces, dipole-induced dipole forces, and London forces all fall under a broader term known as van der Waals forces. That's all you need to know about van der Waals forces. The three key ones to know for your exam and to know well, to be able to identify, to be able to compare are these three: hydrogen bonding, dipole-dipole forces, and London forces. But these other forces are out there. You might want to just have seen their names and be aware of them and know that these three that I circled, technically anything with a dipole, and London forces, any combination of those together falls under the umbrella term of van der Waals forces. So that's hopefully a clear enough overview of hydrogen bonding and its implications for water solubility.